So we've just learned how to do one sample tests of continuous data by hand. So these tests were the z-score test or the t-test. In most cases, though, we actually have the vectors of data, and thus we don't need to calculate some of these things by hand. We can let R do it. So let's move on and start to learn how R can perform these tests for us. So the setup that we're going to use is this. We think we found a new species of flatworm, so we measured the length of the worms and compared it to the average length of all of our known species. Our question is, does the average length of our sample suggest that the flatworm is this new species? Data is available as flatworms.csv. So what I want you to do is to go to Blackboard, get the QMD file that we have, and go ahead and import our data set right up here. And I'll give you time, and then we'll come back. All right, so welcome back. I've already read mine in. I've copied and pasted it up into this section. And now we're about ready to go. But before that, I'm just going to go ahead and run this entire chunk because we're going to be using these in a minute. The library will come back to this section. I have standard error and bootstrap confidence interval. We won't get to this in this presentation, but we will later. We'll continue this QMD file after our exam. And of course, the sign test, we'll leave it as is. So we have our data, and based on our question, we're going to have a couple steps for our analysis. So we have our data set. First thing we should always ask is how many variables do we have and what type of variable do we have. Second thing, so in our data set, I could see we have one variable, and that variable is continuous. The next thing we then ask is what test options are available. Well, we know we have a z-test and we have a t-test. And right now we have a sample, we have our vector of data, and we're trying to compare it to a mean, so it looks like we're going to be comparing a t-test. And then based on that test, we have to ask, okay, what are the assumptions of this test, and have we met those assumptions? If our assumptions are met, then we're going to go ahead and perform the test and make any conclusions about our data based on the results of that test. If the assumptions are not met, then we have to ask, what options do we have? Are there other tests that we can run? Could we somehow transform our data in some way to make our assumptions met, etc.? There are several things, and that's what we'll talk about later on. But for now, let's proceed to our data. So we know a t-test has two assumptions. Data are random and independent, and data are normally distributed. We're going to check our normal distribution using a function in the car package. So let's go ahead and get the car package loaded. There are a few ways to do this, and no matter what way we choose, we're always going to have to get the code into this box. So I can go down to my packages. I can find the car package. Let's see here. Mine is located right here. So I check that. Gonna get that copied and get that pasted up here. So every time I open it, car package is going to be loaded. I have my standard error and bootstrapped, and now I am about ready to continue with this presentation. So we know we want to run a t-test because we're testing if sample mean equals some value. We have a population mean, but not the population standard deviation. Thus, we're going to have to approximate sigma using the standard error from our sample. Our one sample t-test has the null assumption of that our sample mean is equal to our population mean. So bar x is equal to mu. And the alternate, based on our initial question of is our flatworm sample part of a known species, we are setting up our alternate as being our sample mean is not equal to the population mean. And of course, with a one sample t-test, we could specify direction as well. Now, just as a quick review, if we were going to do this as a word problem, we're going to have to assume that all the assumptions are met. Then we'll calculate our t observed using our t observed equation. And then we'll calculate our p-value using the pt function with n minus 1 degrees of freedom. Now, if it's a one-tail test, this gives us our p-value. If it's a two-tail test, then we multiply this by 2. If, however, we have a data vector like we do, we have to do things a little bit differently. Now we don't assume the assumptions are met because we actually have our data and we can check the assumptions. So we're going to check these assumptions. If our assumptions are met, then we'll use t.test to obtain our test statistic, degrees of freedom, and our p-value. If the assumptions are not met, then we'll have to find an alternative method of testing our null hypothesis. So there are two assumptions. Data are random and independent. We're going to assume that this is 100% true. And we're going to assume this for all of our tests this semester. The second assumption is that data are normally distributed. This is the assumption that we're going to test, and we're going to be testing this for a lot of our tests moving forward. So the question is, how do we test for normality? We have a couple of different options. But before we get there, let's talk about why this matters. So if the data are random and independent, and if our data are normally distributed, then our t observed will follow a t distribution with n minus 1 degrees of freedom. If we don't follow the assumptions, especially if we're not normal, then our t observed will not follow a t distribution. If we don't follow a t distribution, then we'll be wrong. So, for example, look at this graph. This is our actual sample. This is a very skewed sample. So we are skewed right, leaning left, which means we have an excess of points down on the lower values than what we should have. If we were to take a sample, take repeated samples from the skewed distribution and calculated t's from it, and looked at all of our distribution, so this would be a null distribution, the histogram, what do you notice? One, it looks like these bars are following our blue line, which is our predicted t distribution. But I'm going to point out that when you're doing an overlay like this line should hit the middle of the bars. And what we're seeing is that we're not. We're actually, the middle of the bars is falling to the left of the line up in our negative region and left of the line in our positive region. So we end up with many more values, many more t observed values in our negative region than what we should have if we followed a t distribution. And we have fewer t observed values in our positive zone than what we should get from our t distribution. And that means then if we calculate a p-value looking at area under the curve, we're going to be wrong. There's way more values that we should be counting down here than what we would actually count from the actual t distribution. There's way more values that we would count up at the upper edge than what we actually observe. So this is all getting to the point where, yes, our p-value will be wrong because we're no longer following a t distribution. So since we have to check normality, what are our options? I'm going to present two different methods of checking normality. And instead of saying testing normality, I'm going to use the phrase assessing normality, because a graphical method is the preferred method, and it doesn't really give us any sort of p-value against which we're testing. So we have a graphical method, quantile plots. This is going to be a preferred method. And we have a Shapiro-Wilk normality test, which is a test. This is going to be much less preferred. However, if you have a reviewer that says they want a p-value, then this is the one you're going to have to use. So let's start with our graphical method, the quantile plots. If you go back to discussion of our continuous distributions and normality, I introduced this idea of quantile plots, where we plot observed quantiles against expected quantiles given the mean and standard deviation of our data. If our data are normally distributed, then all of our observed points should match up with our expected points. So all of our points should fall on a straight line. Now, when we look at this, we do acknowledge that points at the end could fall off the line because we're at the extreme of our distribution, and the probability of getting those extreme values is actually pretty low. So we allow some of the endpoints to fall outside of this line. Now, when we do it, it's going to be when we make our figure using the QQ-plot function in the car package, we're going to see that the plot puts up confidence intervals, or what I'll call a 95% confidence interval. This is really going to be useful because with these confidence intervals, if our points fall outside of the line and outside of the confidence interval, it starts to suggest that our data are now normal. If all of our points fall inside that confidence interval, even though they might not be on a line, we'll still conclude that they're normally distributed. The strength of this is that it's super easy to perform and interpret. The weakness is that we don't have any p-value to report. So let's take a look at some of these QQ plots. So the function is QQ plot with a capital P and X. X is going to be a vector of numeric data. We may need the data $ vector notation in order to make one of these plots, not vector variable notations. Note, this function is in the car package. So if you obtained, let's underline it. So if you try the QQ plot function and you receive some error message saying function not found or QQ plot not found, that's why. Make sure your car package is loaded. Our interpretation: if all or nearly all of our points are within the 95% confidence interval, then our data are normally distributed. If points form a curve with the middle points falling outside of the 95% confidence interval, then our data are not normally distributed. So far, so good. Should be super easy. If our points are inside that confidence envelope, we're normally distributed. If there's obvious curvature and these middle points are falling outside, then we're not normally distributed. This last bit, we do allow a small percentage of points at the end of the plot to fall outside of the confidence interval. We allow that, and we'll still conclude that the data are normally distributed. I think seeing this, and with practice, you get a feel for when we start having too many points falling outside. But in general, you'll know if we're looking at the middle bulk of our points. If you need a percentage, I say you maybe allow 5% to fall outside, 5% at the low end, 5% at the high end, and that would be an appropriate amount. So reporting of it, we're going to say we're going to use quantile plots to assess normality, and then we're going to give a conclusion interpretation. Notice we don't have any test statistic, we don't have any p-value or degrees of freedom. It is simply our assessment method, quantile plots, and our conclusion interpretation. So the data are normally distributed or they're not normally distributed. So in our heading, we made two different types of data. We call them dat good and dat bad. So if we go back up and take a look at them, what you'll see is dat good is normally distributed. So 150 data points from a normal distribution, mean 25 standard deviation of 3. We rounded it to 1 decimal place. That's our good data. Our bad data is going to be coming from RF, so from an F distribution. Again, 150 points. Where our degrees of freedom, there's 2. So a degree of freedom 1 is 5, degree of freedom 2 is 50. And then once we have that, we're going to add 25 to it. And we're going to round to 1. So dat good is normally distributed, dat bad is non-normally distributed, and hopefully then we could clearly see the difference. So what we're going to do is make a QQ plot of dat.good to see what it looks like. So we gave the format. Dat.good is already a vector, so it's QQ plot dat.good. I run it, and let's pop this out so we can see it a little bit more closely. And this is what we're looking at. So we could see our observed data plotted against our expected normal quantiles. If we are perfect, we fall along the line, but notice that we're not. We have points that fall outside of the line, which is, again, just random chance. Our data was randomly generated. If we generated it using a different seed, it would be slightly different, but this is okay. And it's okay, and I would conclude that the data are normally distributed because look at all of our points. It falls within this blue shaded region, which is our 95% confidence envelope. Since all of our points fall inside of this confidence envelope, we can conclude that the data are normally distributed. So our interpretation is dat.good is normally distributed. Now, go ahead and make a QQ plot of dat.bad. Pause this video, make it, look at the figure, have an interpretation, and then hit play and let's see what we're looking at. All right, I've got mine. Let's pop this out. So this one is obviously not normal. And let's see it. So you can see that our line or our points is obviously curved here. And you can see that we have points outside of our middle. We've got a lot of points outside of our end. But clearly our data are non-normal. And I would conclude that they are non-normal. Now, just because they are stepped like this doesn't mean that it's now normal. And if all of our steps lined up in a line and we still had some points outside of the blue, I'm okay with that. The reason we see this stepwise pattern is because of rounding. We've rounded our data points and we started getting duplicate values, and that's the reason for the stepwise nature. I think we'll probably see the stepwise nature again in some later QQ plots. So if you don't quite get that, that's okay. Just know if all of our steps appeared in this straight line, and no obvious curvature whatsoever, I'm going to allow some of our step points to fall outside of a confidence interval. But this, clearly non-normal, as it should be. So our interpretation, dat.bad, is not normally distributed. So, in summary, let's review the QQ plots. So quantile plots are great plots for assessing normality. they're easy to perform, and they're fairly easy to interpret. We do have some leeway in our interpretation because even if we do make some mistakes, most of our tests that we run are robust to violations of the normality assumption. So even if we're slightly non-normal, hey, no harm for no foul. We're not really going to make that big a mistake. And in fact, our test and our conclusions from the test shouldn't be that bad. We shouldn't be making significant type 1 or type 2 errors. The downside of a QQ plot is that we have no p-value to report, and some reviewers absolutely want a p-value. And this isn't just reviewers. It could be a primary researcher, it could be your mentor, your advisor, it could be somebody on a thesis committee. Some of them may absolutely want a p-value, and thus quantile plots are out. You can't use it. But generally speaking, quantile plots are acceptable for use. Publications in biology literature, and especially in the ecology literature, which is heavy in math. So quantile plots, definitely strengths, and it is my preferred method of assessing normality. The second method of assessing normality is with an actual statistical test. This is what I would use if I have a reviewer or if I have somebody saying I absolutely need some sort of p-value to report. The test that we're going to introduce is the Shapiro-Wilk normality test. This is probably the most common normality test around. It's built in to SPSS. Very easy to run in SPSS. In fact, when you run a t-test or if you run an ANOVA, all you have to do is check a checkbox when setting that up to say, yes, give me Shapiro's normality test, and it gives the output. So what Shapiro-Wilk normality test is doing is comparing our observed data to theoretical normal data. It then generates a test statistic W that quantifies the difference between our observed and what we would expect if data were actually normally distributed. Now this W ranges from 0 to 1, so if it is 1, it's perfectly normal according to Shapiro-Wilk normality test, and then as we become non-normal, the value gets smaller and smaller and smaller. This is a test where all of our W's, or W's that I typically see, are usually between 0.8 and 1, or 0.8 and 0.999. So for this test statistic, this is an exception to our rounding rules where I always round to 3 digits when reporting a Shapiro-Wilk test. We run this in R very easy. The function is Shapiro.test with x, where x is our vector of continuous data. And then we're going to report it as our test, Shapiro-Wilk test. You could do Shapiro-Wilk normality test. That's okay too. We're going to report our test statistic W. We're going to report P, and we're going to report the conclusion or the interpretation. We do not have a degrees of freedom, and because we do not have it, we don't report any degrees of freedom. So let's come over here and add some notes to our QMD file. Sure, since this is a hypothesis test, we have a null and we have an alternate hypothesis. Our null hypothesis is that x is normal with a mean, with a mean and a known standard deviation. So with a mean and S. Our alternate is that our data is not normal. So our null data are normally distributed based on our sample mean and sample standard deviation. Our alternate is x is not normal. The function that we use is Shapiro.test. where x is the vector of numeric data. May need our data $variable notation if working with data frames, etc. The weakness, I can't even give a strength for this because I think the weakness way overpowers any strength of getting a p-value. And that weakness is that it is strongly influenced by sample size. So if our sample size is small, it's going to be difficult to detect normality. How small? If n is less than 30, it's going to be tough to detect non-normality. I would even say if n is 50, it could be difficult, depending on how normal or non-normal we are. If n is large, then the test will detect slight deviations from normality. And for this, I would say a large sample size is usually 300 or more. So this test is going to detect slight deviations. It would give us a significant p-value, and we would conclude data are not normal. However, we can normally ignore these slight deviations because our tests are generally robust to all of the violations of normality. So as a demonstration of how to do it, let's do dat.good. We know it's normally distributed because we did the quantile plot. So getting a p-value greater than 0.05 will not be surprising. So when I run Shapiro.test on dat.good, this is our output. And the output is great because it tells us everything we need to know about what we just ran. It gives us the name of the test. We ran a Shapiro-Wilk normality test. It gives us our test statistic W, and it gives us our p-value. So again, our null hypothesis is that our data are normally distributed. We may base a conclusion on whether we reject or fail to reject our null hypothesis based on this p-value. So what is your conclusion? So based on our p-value, dat.good is normally distributed. Now for our write-up, we have to report all of our required items. So dat.good is normally distributed. That's our conclusion interpretation. I give the name of the test, Shapiro-Wilk test. Our test statistic, rounded to 3 decimal places. This is the exception for all of our test statistics. And then I report the p-value. So now what you could do is go ahead and do check normality of dat.bad using Shapiro-Wilk test. Give it write-up, and then come back and see how you did. Here's my code. Shapiro.test, dat.bad, super easy. I get my output. I look at my p-value, and remember, our null hypothesis is our data are normally distributed. P-value this small suggests that we're going to reject that null hypothesis, that data are normally distributed, and conclude that the data are not normally distributed. So for our write-up, I've got dat.bad is not normally distributed. Shapiro-Wilk test, I give my test statistic, and I report my p-value. So what are some recommendations for checking normality? Number 1, use QQ plots. That's what I recommend. Do that, and only use Shapiro-Wilk if a reviewer demands a p-value. QQ plots are quick to run, they're reliable, they're easy to interpret, and even if you have some question based on the figure, usually our tests are going to be robust to any violations of normality, so it's not going to matter so much. So now that we've done that, now it's time to start with performing a one-sample t-test. Now that we've learned how to check all of our assumptions, let's move on to the one-sample t-test. We have a vector of data this code was run previously. We have a sample drawn from a normal distribution with a mean of 33, standard deviation of 2.22, and our question is, does our vector actually have a mean of 31? So this is our working example. We're asking the question, does our vector have a sample mean equal to 31? So our null hypothesis is that our sample mean is equal to the mu, or sample mean is equal to 31. The alternate is that they're not equal to 31, so it's going to be a two-tailed test. So before we run the test, as with anything, we're going to check our assumption of the t-test, which is the normality. So the best way to do this is just to go through and run our quantile plot, take a look at it, and this is pretty interesting. You see that we have a small sample size, and this is one of the reasons why QQ plots are so good, is that we can very quickly see that all of our points fall within this confidence interval, and thus all of our vector is normally distributed. If it wasn't, we'd see a lot of points out. We'd see this obvious curve, middle points outside of this, etc. And if we were to run a Shapiro-Wilk test, it's unlikely that we would get a significant p-value for tests like those. So smaller sample size definitely favor QQ plots. So our interpretation at this point, yes, dat-vec is normally distributed. So because it's normally distributed, we can proceed with our t-test. In R, our function of a t-test is t.test. And it has these options here. So t.test is going to take x, a numeric vector, and it may need the data $ variable notation for it. We have to have our hypothesized mean, that's going to be mu, and then we have an alternative. The alternative is either going to be two-sided, which is the default, greater or less. This tells R if we're going to run a two-sided test or a two-tailed test or a one-tailed test. So the default is two-tailed test. But if we set up a direction, then we have to specify either greater or less, and which one we choose is based on our alternate hypothesis. So if our alternate is that our sample mean is greater than the mu, then we're going to use greater. If we're saying that our sample mean is less than the mu, then we'll use less. And note that when we report these, we have to use these quotations around there. So if we're going to run this test, we have items to report. We're going to have to report our test statistic, our degrees of freedom, p-value, and then our conclusion and interpretation. So let's go ahead and run our test. So we're going to run t.test. The vector that we're using is dat.vec, so we don't need data $ notation since we have our pure vector. Our hypothesized mean is equal to 31. That was up here. And then our alternative is two-sided. So we didn't specify a direction. We just said, is it equal to this value? So our alternate is that it's not equal to this value. So I have everything, I'm going to run it, and we get this output. So you will see in this output, it gives us everything that we need to report in our write-up. We have our test, we ran a one sample t-test. We have our test statistic t, located right there. We have our degrees of freedom, right there. And we have our p-value. So those are the items that we need. The last one that we need is the conclusion interpretation, and that is up to us. So based on our p-value, we have a very small p-value. It's less than 0.05. So because we're less than 0.05, we reject our null hypothesis. And we can conclude that our sample mean, the dat-vec mean, is not equal to 31. So we ran t-test, our t, and I'll do shorthand here, so I'll report 17, 2.97, 2 decimal places, and our p is equal to 0.009. And that's our write-up. Super easy. T.test, our vector, our hypothesized mean, and then alternative. and the output gives us everything that we need. Now, this output has a couple other things that could be useful. So the output tells us the mean of our vector. So if we calculated the mean of dat.vec, we would get 32.96. So we're testing, is this equal to 31, or are we likely to get this value if our true mean is actually 31? And this is saying no. It's too unlikely that we would get a mean like this if our true sample mean or our true population mean was 31. It also gives us the 95% confidence intervals of our sample. And what's important, you can see that our 95% confidence interval does not include the value 31, which, we had mentioned, if our confidence interval captures 31, then our sample mean's probably equal to 31. And we'll talk about using confidence intervals. The other thing is that it gives the alternate hypothesis, which we don't really use, but it's good to see it just to confirm that we did things correctly. All right, so this was a pretty simple example. Let's do a practice. So we loaded the flatworms, and we collected and measured the length of these flatworms. We think this is species A, and species A has an average length of 150 microns. So we ask the question, does the length suggest that our flatworms are species A? I want you to check the assumptions and perform the test. So before we do that, think about what we're asking. We have flatworms, we have length. So we have one variable, it's a continuous variable. We're asking if the mean of that variable is equal to some number. So we are comparing a mean to a hypothesized value. Our test option at this point is a t-test. So we have our vector, so we're going to use it. So what I want you to do is go ahead, write your null and alternate hypothesis, check normality, perform the test, and have a write-up. So pause the video and go do that right now. All right, so let's review. We collected and measured the length of flatworms. Average length of species A is 150. Does our length suggest that our flatworms are species A? So our null hypothesis is that our sample mean is equal to mu, or our sample mean is equal to 150. Our alternate is that it's not equal. So based on this question, we're either species A or we're not. So this will be a two-sided test. Our normality assumption, just going to go ahead and do a QQ plot. I'm going to pop this out so that we can have a much better view. So I can see some slight curvature here. However, our key for interpreting these graphs is that the points have to be inside of the confidence interval, and we have a couple points out, but these are at the extreme end, and I'm going to be okay with that. This one may or may not be, but by and large, the entire center is in there, and that's good. I'm going to consider this normally distributed. Even if it were slightly non-normal, that's okay. Our t-test does pretty well with non-normality. So I think our interpretation here is that our data are normally distributed. So flatworm length is normally distributed. And then we have our test, t.test, flatworm length. So we now have to do data $sign variable notation. Our mu is 150 and alternative is two-sided, and we get our output. So we have everything we need. We look at our p-value, that's super small, suggesting we have to reject our null hypothesis and thus conclude that our sample mean is not equal to 150. So our sample mean would be equal to 150 if our sample came from that species, and thus our sample is not equal to that species. So let's go ahead and take a look at our full write-up. All right, so for a full write-up, we're summarizing the entire test, including tests of our assumption. So for my full write-up, I'm going to say we collected length data on flatworms to determine if our sample is species A. It kind of lays out our biological question. Quantile plot suggests that flatworm lengths are normally distributed. There's our check of the assumptions. And then for the write-up of our t-test, a t-test suggests that our flatworm average length is not equal to the mean length of species A. I gave our test statistic, degrees of freedom, gave our p-value, and then gave our interpretation linking back to our original biological question. So this would be a full write-up, and just so you know, if I ask for a full write-up for a problem, this is what we're looking for. If I just do a write-up of our test, then it's just this part that's highlighted. So let's do one more in-class practice, and then this will be the end. So we're going to use a built-in data set called penguins. In this data set, we're going to examine the flipper length of chin strap penguins. So what are chin strap penguins? It's these guys. Notice the chin strap. Pretty cool. So I want you to run this code. So penguins is built in. We're going to run a subset function on penguins, and we're going to save the output as chin strap. So you can pause and you can get this code into R. What this code is going to do is that it extracts all rows from this data set that match a certain condition. And the condition that we're matching is all of the rows that have chin strap in their species column. So if we click on chin strap and open it up, you'll see that we have a species column here, and all of these rows are chin strap. Well, in the penguins data set, it has two other species in there that we don't really care about because we're going to be running a one sample t-test here. So I have the code explanation here. We're going to be using subsets in this class. We'll use it again. So this will be the first time you see it, but it's not going to be the last. So once we run the code, you should have chin strap appear up here, 68 observations with 8 variables. Now with this subset function, it's going to take a data frame and it's going to output a data frame. So if I do summary of our data frame, we get something like this, and I'm going to open this up. So you can see that our original data frame had 3 species. Adelie and Gentoo had 3 different islands, Bisco, Turgerson, and Dream. And then it has bill length, bill depth, flipper length, body mass, sex, and year. And if you wanted to know more information about this, just go see the help file for Penguin for the data set. So our focus here is that Adelie penguins have an average flipper length of 189.95. In our chin strap data set, our average flipper length, and just go back up here, our average flipper length is 195.8. So I want to know, does our chin strap penguins have longer flippers than the Adelie penguins? So what I want you to do is check the assumptions and perform the t-test. And then, when you're done, have a full write-up. Oh, I should say, what's an Adelie penguin look like? Adelie penguin looks just like this. And for comparison, here's our chin strap penguin. So Adelie penguin, no chin strap, deeper black on the head. We got our white given the chin strap. So go ahead, work on the assumption and the t-test and the full write-up for this question. So hopefully you had a good time, easy time doing this. So I went ahead and wrote our null and alternate hypothesis here. So our null hypothesis is the exact same. Not sure why that did that. But our null hypothesis is the same. Our sample mean is equal to mu, or our sample mean is equal to the hypothesized value. Our alternate, though, is different. So we've actually set up direction with our biological question. We asked, does our chinstrap penguins have a longer flipper? So our alternate is that our sample mean is greater than mu, or that our sample mean is greater than 189.95. This changes our test, so now we're running a one-tailed test. And it's going to change how we report our results. So since we're asking about direction, we're going to report on the direction as well. So our assumption, normality, we make a QQ plot. It varies. It's very clear that this is normally distributed. Everything falls within our confidence interval. So that's good. So now that allows us to run our t-test. So this is a dated $ variable notation because flipper length is inside the chinstrap data frame. Our hypothesized mu is 189.95, and we've set up direction, so we'll use alternative equals greater. We get our output, and we have everything we need for our write-up except our interpretation, and that is up to us. So based on this p-value, it's less than 0.05, it's very small. We would conclude that our sample mean is not equal to 189, and thus we're going to accept the alternate that our sample mean is in fact greater than 189. So our flipper length of the chinstrap penguins is longer than the flipper length of the Adelie penguins. So for our full write-up, I went ahead and introduced our question. So chinstrap penguins appear to have longer flippers. To test this, we first confirm normality of flipper length using quantile plots. That's sufficient. We said exactly what we did and what we found with our assumption. And then a one-sample t-test was performed. There's our test. It confirms that chinstrap penguins have longer flippers than Adelie penguins in this data set. There's our conclusion interpretation linking directly back to our biological question. Our test statistic T, 6.79, our degrees of freedom, 67, our p-value less than 0.0001. So that wraps up this video. This is all going to be on our exam on Monday. Look for any sort of presentation or Blackboard announcement that alerts you to extra practice problems. We'll do a few more just to make sure you're comfortable with doing t-tests with vectors. And then we will proceed with what happens when we actually violate the assumptions. What are our options?